Right, so we're presented with this piece of equipment that the only interface to it seems to want a password to get into a menu. So advanced options, it's asking for us to enter a password that we don't know. We can guess it's probably 3 digits because that's what it's letting us enter. And on the other board we can't even get into that menu. We just press the menu button, it says menu access is disabled, so we can't really get anywhere. So I figured the way to attack this is to read the ROMs and disassemble the code and see if we can actually figure out what password it's looking for. Right, the software is in these. These are basically they're EPROMs, but they're one-time programmable because they're in a plastic package. They're sort of the old UV erasable type. At the time you could actually buy ceramic ones in this package, but they were very expensive. So obviously for a production thing they just used these, and on an expensive piece of kit, you know, if they had to throw away the chips and program new ones for a software upgrade, that wasn't really any big deal. This was really before flash memory was available. For reading these I just use this. This is just a homemade adapter with a PLCC socket soldered onto a header that goes into the DIL ZIF socket of the universal programmer. You can actually get ZIF sockets. This is actually a ZIF socket for a slightly different package. It's actually this one, which is a leadless ceramic package. And again, that just sort of sits in there, and then the lid goes down and clamps it down. But I don't have a proper ZIF for these, so I'm just using this because I'm not planning on putting these in and out too many times. That's not really a very big deal. And so these SST flash chips got the same pin out as the EEPROM, but obviously the advantage is that I can reprogram these as many times as I like. And for getting these in and out of the sockets, it's quite important not to just try and screwdriver them out because you can bend the pins. And what you ideally want is a tool like this, which lifts both sides. It grips the two sides and then lifts it. So you just insert that into the two sides, insert some sort of pressure this way to grip it, then sort of give it a squeeze, and also if you give it a little wiggle on its way out, that helps it out a lot, and then it just comes out like that. It's very important to take these things step by step so you don't get confused by sort of things, unexpected things. So the first thing to do is just to program the standard code into these flash ROMs, run the system up. As you can see, it all starts up no problem, so that all works. The second thing, when you're changing code, it's not uncommon for these things to have a checksum in the ROM, so that when the thing starts up it checks the ROM and it then gives you an error message if the checksum is wrong. So the second thing is just to make some fairly trivial change just to see whether the system works. So what I did, I just found the advanced options menu, changed a few letters on it, and you can see it's now showing those changed letters, not showing any checksum error. So it looks like we can make changes to this ROM without things totally freaking out. So the next step will be just to go through all the bits where it's saying invalid password and just patch that code out so it just doesn't execute whatever the password is, it just passes it regardless. I'd like to say a quick thanks to the people that sent me disassembly listings. I'd identified that there's a package called IDA that supported the i960 instruction set, so I put the ROMs online. A few people sent me some disassembly listings because they had access to that package. There's generally quite a lot of conventions in opcode names, so you don't really need to know that much about the instruction set quite often. Once you're sort of vaguely familiar with a few different bits of machine code, you generally find that you can just get a rough idea of what's going on just by looking at the code. For example, here you've got sort of LD is fairly universally used for load, so load possibly accumulator or load absolute or something. STO, again, that's store, move. For example, here move register to register. The move instruction, sometimes it's move source to destination, and sometimes it's move. It's the other way around. There's no real convention. That's one thing you do need to either look at the instruction set reference or just try and figure it out by context by looking at the instruction. And things like call, B for example for branch. So you can quite often get a rough idea just by looking through the code. So a good disassembler will do things like split it into function sections and take some of the donkey work out, generating cross-references and so on. The other issue is when you're disassembling from ROMs is you don't necessarily know what address in the system those ROMs actually sit at. Sometimes you can figure that out by looking at the datasheet of the processor. For example, if the boot vectors start at address 0, then it's fairly probable those ROMs start at address 0. Similarly, if you've got boot vectors at the top, for example, like a 6502 system, the chances are those ROMs sit at the top of memory, and you can probably figure out where they start from the size of of the ROM relative to the top of memory. So the first step really on doing anything like this is to get a full disassembly, preferably with a disassembly that's smart enough to know, for example, it doesn't try disassembling data sections, so things it can't make head nor tail out of. It actually marks out, figuring out this is probably going to be data rather than code. Because one problem is a lot of the time you've got like bits of code and bits of data all over the place, and if a disassembler tries disassembling through data, it will produce rubbish, which, okay, you can quite often identify that the code just doesn't make sense by what it's doing, but you can also find on any system that uses different length instructions it can get out of step, so it may sort of go part of the way through some data and then start disassembling and just get out of step with itself, so it can take a while before it resyncs, so you'll actually lose some of the real code. But this disassembly listing is pretty good. It's sort of split up into sections, it's cross-referenced, it's fairly nicely formatted. The only thing I don't like is it doesn't include the actual opcodes. That may well be an option that just wasn't enabled at the time, but it's nice to have, as well as the address, the actual bytecodes that it's then disassembling, because that makes life a bit easier if you're then trying to patch them. And also, if you don't have the instruction set code, you can actually look at the codes generated by all these various instructions and find out quite a lot about the instruction set. If you don't have access to that, or you just can't be bothered to look it up, it's quite often easier just to find some code, look at it, and you can often work out the structure of the instructions and so on. Right, so what we know about this is that when we type the wrong password in, it gives us the invalid password string. So the first thing to do is actually try and find that string in the disassembly. Now, because this has gone through quite a clever cross-referencing disassembler, it not only finds that string, but also tells us where else in the code accesses it. So there's a cross-reference to here. Even when that's not the case, I've quite often in the past, a simple trick is once you've got a disassembly in a text file, just doing a simple text search on the address can be a very effective way of just finding cross-references to it. Because if there's a direct reference to that address, it will appear in the hex. So you just sort of look where the address is and do a text search. But we don't have to do that because this software, I'm not sure how much of this has been generated automatically and how much has been done by the guy that ran this through the disassembler. Most, a good disassembler will let you, assign meaningful names, but things like taking ASCII, it's fairly reasonable to assume that an assembler could be clever enough to say, that's a bit of ASCII, let's assign a fairly meaningful label name to it, so you can easily find references to it. So if we now take a look for references to that label, again I'm just doing this with a simple text search in a text editor. It seems to be about 4 locations where it's being accessed. So let's just take a quick look. This is loading the address of that invalid passwords message. Although that's called Parcel Manager, I think that's been renamed. If you look through it, that appears to be called almost every time there's a reference to text. I think that's just like a print message. So if we now look at where this code is called from, we can actually see above here we've got a comparison here. So it's doing some sort of comparison, not paying too much attention at this stage to exactly what, but I think that means compare immediate, branch if equal to there. So if R4 is equal at that point, then it branches to the invalid password message down here. Otherwise, it goes down here. Now, we could spend a lot of time trying to figure out, well, how does it arrive at that value of R4 and just keep tracking the code back, but that gets pretty tedious. So I thought actually it's going to be a lot easier just to knock this all out. So if we just literally replace all this section with null instructions, we could sort of, for example, add a branch in there. The problem is a lot of processors use relative branching, which is a bit of a pain in the ass to work out the offset if you've not got a proper assembler. So what we should be able to do here is literally take all this code and just replace it with no op, so it will literally just fall straight down to the place it would have gone to if the password was valid. Now there's 2 references to invalid password here, there's one down here, so what I guess is we've got 2 checks going on. One is probably that the right number of characters has been entered, and then the actual check of the actual content of the password. So we've got the first check here. There's also a reference here, cancel. That's again if you press a cancel button while entering the password, we get a cancel message. So this clearly is code relating to this password thing. So again, if we go down here to this second bit where it's checking here, so again it's doing a little bit more here. So it's doing a compare and branch if not equal seems to be going down here, and this location here 35434 is actually branching directly. It's obviously not very efficient compiler because it's actually branching sort of straight ahead. So what I'm guessing with is it's probably doing some comparison on the password here and just jump it. It sort of looks like it's, yeah, when R4 is 0 it's going to 4, so that's probably when it's completed all the parts of the password. Again, one of the problems with disassembling is you get subroutines and then they call other subroutines, and it gets really difficult, especially for something that's been done with a high-level compiler. The compiler will be generating all sorts of code all over the place. So I think what we're going to do is literally just take all these invalid password stuff and just force it to just go straight to the bit after that check. So I just need to take a quick look at the i860 instruction set and find a suitable knot, but bear in mind it doesn't necessarily actually have to be a knot. Quite often you've got instructions which are clearly only have very limited local scope, for example sort of loading registers and comparing registers. So we could probably actually, if we can't find a suitable knot, just find something which is not going to have any effect on this particular bit of code, so we can see what happens after it. For example, if it's about to load, if the next thing it does is load a register, then any other instruction that loads that register isn't going to have any detrimental effect, so we could use that as a knot. So just take a look at the i860 instruction set and see what we can patch into this to disable this stuff. Right, I've had a quick look. I can't immediately find a comprehensive instruction set reference, but one thing I did notice, I initially sort of ruled out initially looking at creating new branches just to jump over the code, because quite often branch instructions, they tend to be relative and sometimes they've got weird offsets. For example, particularly on pipeline processes you find those offsets, so calculating them by hand can actually be quite tricky. But in fact this looks pretty straightforward. I just had a look at a few sample branches. So for example, if we look at the that one that was jumping pretty much straight ahead, so this one here, this is located at 35430 and it's just jumping to the next location, so it's, all the instructions seem to be on 4-byte boundaries. So this is jumping ahead 4, and if we actually have a look, unfortunately this disassembly doesn't include the actual code bytes, which is a little bit annoying, so I've just listed those separately. So if we look at 35430, what's actually there, we've got this 08, which is the opcode, and 04, which is the offset. So the offsets do actually look to be pretty straightforward. If you just take another look at another one just to verify that, obviously because they're jumping forwards they're positive. If they're negative then you've got to mess about with two's complement and so on, but fortunately all the things you want to bypass here are forward jumps, so they should be fairly easy to patch out. So if we take a look at this one here, this is located at 3540C and it's jumping to 3544C, so it's jumping 40 bytes ahead. So if we look at the code for that, 3540C over here, 354C, that's here. Again, we just see the 40, so the offset is really very simple. So all we need to do to bypass these two checks, so if we take this first one, what we want to do is where it would be jumping to this part here, which is here. So this test is jumping to the invalid password message, and this one is just carrying on doing the next test. So what we basically want to do is duplicate this branch here, and we need to adjust the offset because the code is 4 bytes earlier. We need to add 4 bytes to the offset. So if we first find this instruction 353FC in our listing, which is here, so what we need to do is take this and just copy it to the previous location. I've actually already done this. So whereas that's got an offset of 14, the offset is now 18 because it's jumping from an earlier place. So that's now basically effectively copied that instruction here, so it's disabled that comparison. So if we now go down to the next bit of password checking, which is down here, so here that's the branch to the invalid password message, and that looks like it's the branch to the carrying on. So again, what I want to do is basically set this again we're copying this branch to the good place. No, sorry, that's the bad place. What we want to do is copy this where it would be saying invalid password to this address here. So now this is a different instruction, it's not an unconditional branch, but hopefully the offset, we should be able to see the offset and tweak that. If we work on the assumption that the effect of it, we don't really care what this instruction is doing, these are always assuming that the password is just validated and then it's not being used again. Obviously if it's making use of it further on, this technique might not work. So what we're going to do is change that from a conditional branch to an absolute branch to this location, this 35444. So we need to work out what the offset of that should be. So let's just take a look at what the actual opcode of that is. 3542C, which is 3542C, that's here. So what we want to do is create a branch. So we know the code for a branch is an 08, and we need to generate the offset. So the offset will be 35444 minus 3542C, which is 18. So we want to change that to an absolute forward branch with an offset of 18. So it would be 18. Alright, so what we should have done now is change this to a B and then to this 35444, which hopefully is a second password check that it should now pass. One thing that's a bit annoying, because I don't have the full disassembler here, what I'd normally do if I had a disassembler is after I'd patched all these things, I'd then re-disassemble it to verify that I'd actually done it right. Obviously some of these invalid passwords messages could be to do with user IDs and other passwords, so we're just going to go through and do all of them, and hopefully it will never need a correct password for anything. Now we need to program this back in. Now because there's a 16-bit image and we're programmed to two 8-bit ROMs, we actually need to split it out into those two devices. Now some programmer software has a function that will just split one file into two files. This particular software does it by the way the addresses are incremented. So because we're generating two ROMs with also basically interleaving alternate bytes, so we tell it to program every second byte of the buffer starting at 0. So this will generate our odd ROM. So I meant the even ROM, so we now generate the other ROM. So this time again we say every second byte, but we start at buffer address 1. So we generate the pair of ROMs that we then when read together provide that 16-bit image. Alright, just fire this up again and see what happens. Alright, so it started up, so looks like we've got the ROMs the right way round. Let's see what happens when we try to go into the menu. So, advanced options, 5. Now type any old password in. Menu. Hey! And now we have the advanced menu. Right, I've just swapped over to a flat screen monitor because the flicker on that other one was getting annoying. Unfortunately we don't seem to have any setup or maintenance type stuff in here. A few options, the first few options doesn't seem to want to do. I'm getting a lot of sort of option not installed messages on here. Let's see if there's anything that does anything particularly interesting. Right, so there isn't really much doing here. So the question is, how do you get to the interesting bit? So before I start having a look at the rest of the code, I'll just sort of try the usual, just sort of playing around. Let's just see what happens if we press a few other buttons. And I was just sort of tinkering around. And from the menu, if you press one of the other buttons, you get this little message appearing briefly. Service mode password. So yes, that sounds interesting. The question is, how does it want us to enter it? Maybe you have to hold it down. Again, we'll just try any 3 digit. So I should try, we did identify 344 as a possible password. Let's just try that. Oh yes, this looks like what we're looking for. Right, just for amusement, I just stuck another board in that's got the original software, because I have a feeling that all that password patching wasn't actually necessary, because we'd already found, someone had found that 344 password from a Chilean training manual. So once the menu's up, just by pressing and holding one of the buttons on here, the high pen button, and typing in that 344, we get into the menu. So it turns out the 344 was actually the password all along. We just didn't know the method to get into it. Maybe if we'd actually translated that Chilean manual, it might have actually said that you have to hold the high pen button down in menu mode. And why do they use 344 as a password? Well, E, G and G. That's interesting. We seem to have set the menu access disabled now. There must be some way of getting back into the menu to re-enable it. Some random button pushing later, I figured out how to get this thing. If you just press menu and then press 0, sorry, hold 0 and then press menu, that then gets you into the menu. So we can now, this is back on the original PCB that had the menu access disabled, so we should be able to, now we know how, change that option. So we go service mode 344, bang, into there, thank you very much. Right, it turns out the password that it was looking for to get through the advanced options menu is actually a system password that's actually settable within the engineering mode, and this actually appears to be set to 911. So knowing that 344 will get you into this menu that then lets you set or find that password, and that's the one that gets you into the advanced menu without having to do any software hacks to it. But as we saw, it doesn't actually let you do a great deal of interesting things. Right, so we seem to be fully into this thing. We've got access to all the maintenance stuff. I'm going to leave playing with that and going through that and trying to get this thing working to another video. I'm running out of time at the moment. So there's a few interesting lessons to sort of learn about this. Firstly, reverse engineering is not all about sort of just diving in and disassembling things. Quite often it helps to actually think about how this thing is used. For example, this sort of machine is just deployed all around the world. It's been serviced by lots of different people, so for example there probably isn't like a special service box that you need to plug in. It's almost certainly all going to be done by the keypad. Similarly, you turn the thing on, it says menu access disabled. Well, how is that re-enabled? There's a good chance that it is actually done by the keyboard rather than some extra, like for example having to pull the cover off and flip a dip switch or something. It's fairly unlikely if you think about the logistics of using this thing. I obviously, I didn't spend enough time just methodically doing lots and lots of buttons, not so much random button presses, but trying different permutations in a sort of semi-methodical way. So if I'd have spent a little bit more time on that, I could have pretty saved all that hassle of doing the disassembly. If I'd have literally just noticed that when you press the high pen button in the first menu, it actually asks for a password, and that password, okay, we're lucky in that someone managed to find that, but that's where maybe if you knew it was a 3-digit thing, it might have actually been quicker just to do an exhaustive search of the whole number space. It's only 1,000 permutations, or at that point maybe you dive into the disassembly and see if you can find anything. But we seem to be back into it now, so we'll have a further play with it and see if we can actually start x-raying some things.